So my name is Karim Douieb. I'm a data scientist, co-founder of Jetpack.ai, which is a data science company based in Brussels, Belgium. We do custom application for a large panel of customer in various fields that help them to better operate in their day-to-day life. And so today it's not going to be about this. It's more going to be about explaining how we use observable notebooks to explore visuals, do some experimentation and everything. And more specifically, this talk is going to be about election maps and how we decided to take on the task of visualizing the latest US election in original map. So if you've heard about me in the past, it's probably based, it's most probably because of this tweet, which was a response to Laura Trump back in the days in 2019. She was implying with the map she posted that most of America was voting Republican. And so I decided to, I thought that this map was misleading, and I thought I could redesign it. And I posted this map, which transform our map, which morph and all the county into bubbles, which size is proportional to the number of voters in each of them. And I think this map is a more honest representation of the popular vote in the US election, and give a better understanding of how people have voted during the election. The talk that I'm doing now is not going to be about this. I think although this map animation is great and succeeded widely, more than expected, I don't think this is the best way to represent the US election. At least it doesn't provide the necessary insight of the outcome of the result, just because the popular vote isn't the way the election's working. So I'm going to talk about something else that we designed using Observable. But first, I'm going to talk about how traditionally the US elections have been depicted, how cartograms is entering the game in the mainstream media. I'm going to talk about our alternatives, how we implemented it using Observable and using the collective knowledge of the community, and then conclude on some takeaways. So far, during the election night, after the election night, what we've seen in the mainstream media, I've collected a few of the main entry page of those mainstream media. What you're seeing here is the traditional maps describing the election. So it's basically a US election, US map divided into states, because that's where the elections plays at the level of the states, not the county, like we've seen with Lara Trump. Each of the states are color-coded by the majority of the party that win the election. And then in those mainstream media, more and more you would see an option to switch to another representation. And those kind of representation that you can see are called cartograms. Not all of them were providing this kind of view, but you can feel that it's something that is becoming more and more relevant to display the result of the election. So if we focus, for example, on the New York Times result depiction, what you see is that you enter with the main traditional US map, and then you have a few options that tell a different story. And you can go from traditional to cartogram just by one click. And what you see here is a cartogram that is pretty specific to the style of the New York Times. What you see is that each of the newsrooms have used a variety of style and approach that are all different somehow. The one used by the New York Times is provided by those kind of little squares. So as you know, US election is you basically have to gain the majority within one state. And if you win the majority within the state, you win all the electors associated to it. And at the end of the day, what you need is the most amount of electors. And the electors within these cartograms are associated to those little squares. Using this, you can then see how many electors are associated to a specific state. There's label to help you to understand that this is New Jersey, for example. And sometimes the shapes is by its own is helpful to understand, recognize the states. So that's great. Nowadays you see traditional and cartograms, but why do we even bother with cartograms nowadays? And the reason is pretty simple. I'll try to go to explain it. The main reason why you would see a cartogram is the following. So if we focus, for example, on those two states, Montana and New Jersey, you see they're quite different in size. So the area of Montana is almost 17 times larger than New Jersey. But within the election, New Jersey is much more important because it has 3.5 times the amount of electors. Montana has only 4, whereas New Jersey has 14. So within the election, New Jersey is much more important than Montana. Although when you look at the traditional map, your brain is directly providing or associating more importance to Montana because it's visually more important. The area that you see is larger for Montana. So your brain is tricking your interpretation, and that's why cartograms come into play. Instead of representing accurately the geography of the states, we use different type of approach where we morph the shape of the state in order to be more associated to the electoral importance of each state. So New Jersey now has those 14 squares that represent all of the associated electors, whereas Montana has only 4. If we try to get the pros and cons of traditional map versus cartograms, of course, geographically, the traditional maps are fully accurate, whereas cartograms are often distorted, maybe harder to recognize the shapes of the states and so on. But on the other side, cartograms depict a more accurate view because it's highlighting importance over emphasis area in the case of traditional maps. And so in terms of familiarities, the general public is much more familiar, of course, to the traditional maps. That's the usual way the results are displayed. So they quickly understand what this is all about. Whereas with the cartograms, it's much less familiar for them. It requires often some explanation. It's not that easy to interpret for them. Whereas the traditional map, it's easy to interpret. You know which state has been won by which party, but somehow it's misleading because you associate, as I explained before, you associate too much weight to larger state. Sorry. So here I'm not going to talk about the exploration that we tried to do. It's another type of cartogram that sits between the traditional and the cartogram, and we try to take the best of both representation and try to overcome some of the downside of each of them. So this is the the experiment that we conducted. This is the visual that we designed to show the latest US elections. What you see here is an animated version of it. If I fix it, what you see is sort of mix between a traditional map and a cartograms. Each of the states shapes remain. It's the exact geographical shape of each state, but then it's split it into it's morcellated into individual states, and then the size of it is rescaled to in accordance to the electoral importance. So California has a huge impact on the election, and so the size of it is quite big. New Jersey, which is this tiny state, gets much larger, and then all the smaller states in terms of electoral importance are rescaled downscale to in accordance to their weight. And then the number of electors is visible through those kind of subdivision. It's called Voronoi subdivisions, which help to quickly assess how much elector is associated to a specific state. And so in terms of quality of these new visuals, you can see that it's geographically it's in between. It's not fully accurate because I mean, you can still recognize US as a whole, although it is a bit distorted. But like the shape of each state is geographically correct, so it's not fully distorted. You can still recognize geographically the shape of the states, but it's an in between, let's say. In terms of electoral importance, it's like a cartograms. The importance of the each state is associated to the area, so you get the proper impression. In terms of familiarity, again, it's you cannot fully understand that this is US as a whole, but each of the individual states are familiar to people. People living in Illinois would recognize the shape of their states easily. In terms of interpretability, it's still easy to interpret thanks to the animation. So this is a key element for the understanding of what we're showing. We start with the traditional representation, and using transition, we can explain somehow that what they're seeing is just a reshaped map of the US election. So thanks to animation, the interpretation gets easier. And in terms of engagement, it's much more engaging in a way that it's new. It's not something that has been seen before, unless you say so, and you point me to another similar visuals. But yeah, this is somehow quite new, and people might be interested because of this fun animation effect. So yeah. And so now I'm going to dig deeper into how we've implemented this using Observable. First of all, I'd like to tell that we basically didn't invent anything. This is not new as such. We just combined together lots of different approaches and put them in other contexts, glue them together in a way to make it possible. So it's all started from this non-continuous area cartograms from the 70s, developed by Judy Olson. Here, she designed this rescaling of the states for US, and the area associated to each state is associated to a metric. In this case, it's just the number of persons above the age of 75, and so each of the states is rescaled around its center point, and then you get a sense of how the distribution of those persons across America. And so what we've just done, and that has been done already in the past, is use this kind of representation in the context of US election, where the metric there is the number of electors. So if we start from the US map, we can scale down each of the states in accordance to the number of electors. By just scaling down, you end up with this. So California is much bigger than Montana, and the ratio between the area of California and Montana is equal to the ratio between the amount of electors in each of the states. The problem with this is that it's too small. There's not enough. There's too much white space, basically. So what could be done? Instead of just reducing scale, we can decide to scale up, growing the size of some states, and scale down the size of the less important states. And so by doing so, you end up with something that is much more filling, and it's going in the better direction. The only issue is, of course, what you're seeing here is all those small states that have a large weight in the election tend to grow too much and overlap each other. So the idea then was to how can we fix this? From my past experience, often when you have to deal with this kind of stuff, there's an utility function in D3 that's called force layout simulation that allow you to deal with layering shapes, in this case bubbles, where you attach a target position for each of them, and you say you can attach also or define some constraint, like the bubbles don't have to they have to repulse each other with a certain type of force, and then you can also control the fact that they cannot overlap. And so by applying this sort of algorithm, you can sort of place shapes that don't overlap each other. Of course, here the issue is that we're dealing with irregular shapes that are states. So how do you use those kind of force layout simulation with other shapes? And so that's where the community of Observable, and we mentioned it in the talk before, is getting super useful. If I search for force layout with shapes, and I search for that, first thing that comes is something that's do a layout of shapes, irregular shapes. This is regular shapes, but still you can do that. And there's maybe square. You can search for this rectangle. Well, there's other stuff that where rectangle could be used. So what I've done is basically take each of the state shapes, create a bounding box around it, and then just apply this alternative implementation of the force layout with rectangles. And what you see here is that it's placing automatically the squares that are encompassing the states, and then you get a proper layout with no overlap. Of course, this is an initial stuff. You could see that there's still some overlap and stuff like this. So at the end of the day, what I've done is simply to readjust manually the position of each state using Figma. So yeah, sometimes you have to find the right threshold between doing everything manually, doing everything programmatically, and just tweak it, tweak the design, the style, and stuff like this with another tool. Also, it was super useful to place the labels. And so that's what I've done at the end. So at the end, we have this kind of map, which is great. We have all the states that are shown, that are color-coded by the majority of the party. Then each state has an area that is directly related to the electoral importance. It has this familiar state shape, so we satisfy the geographical constraint of it. But then what about the number of electors? How can we show this? Of course, I showed you the Voronoi subdivision that we created there. But how do you do that? So the real issue there was to create this, find an algorithm that could do that. So basically what we need to do is split an irregular shape polygon into roughly the same area of roughly the same size. So the number of the number of subdivision that we want corresponds to the number of electors associated to the states. One way to do that, I didn't know how to do that. I didn't know. I mean, I had a few naive ways to do it, which is just split in half using a horizontal line and then recurse, doing a divide and conquer algorithm. Wouldn't end up great with just stacked layers. So I searched for ways to do that, and I stumbled upon Stack Overflow answer from Topi Tukhanov, who proposed an implementation of another algorithm using QGIS. Looking at this, I told myself, okay, this is great. I have all the steps needed. I can just re-implement this into Observable, and that's what I've done. I've also, what's great about Observable notebooks is that you can actually explain all your process approach. People can comment on it, and I can expose that easily, showing all the source that I got, the inspiration and everything. So I'll go through the notebooks that I created. Here, again, what we need to do is split the shape of the state into equal parts. So it starts by placing random points within the shapes. Again, there, the way to do that naively was to create a bounding box around the shapes and then put a points randomly, random x, y, and then use turf.js to check whether the point is within the polygon. If not, we discard the point and we do it iteratively until we get a certain amount of points within the shape. This is rather slow. It's a naive approach, which works well, but it's really slow. But then again, you go search on Observable, and you end up in another notebook where Benjamin Smith provided an algorithm to create that density map, which really starts with an algorithm to place randomly points within shapes in a really efficient way. And so all I did was take his algorithm, which was basically, just to quickly enter into the technical details, splitting the shape into triangles, and then randomly place a point within a triangle is easy. You just have to select the triangle according to their area, and then you end up with a quick way to fill up randomly the set of points within the shape. What we needed to do next is to create a clustering of those points into a certain amount of cluster that corresponds to the number of electors within the states. By doing a k-mean, by implementing a k-mean algorithm, you could see that it's splitting the shape, the set of points into several categories that are color-coded. And there you already see that this is almost what we need. We just miss the proper shapes. To do that, all I needed to do is to extract the center point of each of those clusters. That's the big point that you see there. And then applied compute the Voronoi diagram using turf on those points. And what you see is a proper subdivision of the state. Everything that is missing is just clipping the faces of the Voronoi shape using turf again. And we end up with those subdivisions that are roughly equal in size and are of a fixed number. And so basically, I've used that to subdivide the full states within electors. All right. And so now to conclude with a few takeaways, I think simple and effective visuals takes time. You've seen it. You need to come up with sometimes fancy algorithm to make it look simple, but behind the hood, you can feel that it's complex. But still, they're really fun to do, and I think they're rewarding in a way that you end up creating something that is not seen before, although you combine together stuff that people have done. And then the idea is just to give it back to everyone, creating those and Observable allowing you to do that. You can create notebooks to share your result with the world, and people can take over and do their own thing. And so this relates to the Observable community, which is really a gold mine for algorithm and inspirations. You've seen it, or we use it in the daily settings where we need something, we have an idea about how to solve stuff, we just search for it within the notebooks and we find it, we iterate on it, we fork, we adapt it. So it's great on this level. It's what makes Observable so great. It's their community. And as a last takeaway, I think there's always ways to reimagine something that has been done many times before. There's always room for a little bit of creativity that add a bit of twist or interest into something that has been done thousands and dozens of times. And finding inspiration within community in notebooks makes it easier to come up with something new. So this concludes my talk. I hope you liked it, and if you have any questions, don't hesitate to tell me.